In Germany, the Fraunhofer UMSICHT Institute has developed an accelerated H2S biogenic corrosion test to evaluate building material resistance to severe H2S corrosion found in wastewater infrastructures. Microbiologically induced corrosion, or MIC, is another name for H2S biogenic corrosion. The test principle is simple. Specimens are put into an environmental chamber. The air is saturated with moisture and the temperature is increased to 30 degrees C. Then bacteria typical of sewers are introduced. H2S is fed around 50 parts per million alongside bacteria nutrients. Within these ideal conditions chosen to accelerate the H2S corrosion, a biofilm rapidly grows on the specimens and the bacteria transforms the H2S into sulfuric acid, as this occurs in the aerial parts of sewers. It is thus possible to evaluate how building materials will behave in sewer infrastructures. Within 1 year, it is possible to assess the potential durability over decades. Let's see the behavior of different types of mortar specimens exposed to the Fraunhofer UMSICHT test for 9 months. During the whole test, the surface pH is measured once a week, and the weight loss is measured at regular intervals. We are focusing now on the behavior over time of 6 different cementitious mortars. These first results shown here are for the mortar cubes made with ordinary Portland cement, CEM1, and sand. Under the action of the bacteria transforming the H2S, the surface pH rapidly decreases below 1, dissolving gradually the cement matrix. Within a few months, the cubes are crumbling apart. The weight loss after 9 months is 83%. This second set of specimens has been made with the same OPC CEM1 with the addition of fly ash and silica fume. Although such additions are expected to improve concrete durability, it does not enhance protection against H2S biogenic corrosion. Once again, the pH decreases below 1 within a few months, and severe damages are observed. The weight loss after 9 months is 87%. This third set of specimens are made with a so-called geopolymer. Although the manufacturer claims this product is acid-resistant and thus adapted to corrosive sewers, it did not survive the action of bacteria. The surface pH decreased to 0 within 8 months, and the material turned to a muddy texture to the point that the weight loss after 9 months is 100%. A similar behavior is observed with mortar specimens made with a crystallization admixture claimed to protect the concrete sewers from H2S corrosion by sealing the porosity. Cubes are severely damaged within a few months. The pH lowers to 0, and the weight loss after 9 months is 64%. Just beside the previous series of cubes, specimens made with a calcium aluminate cement were exposed. After the same 9 months of exposure, the visual damages are very limited. The cubes have retained their shape. They're still sound and solid. The surface pH stabilized around 3.8 after 3 months. This is because the calcium aluminate cement inhibits the bacterium metabolism, which stops the transformation of H2S into sulfuric acid. The weight loss after 9 months is only 25%. This last series is made with 100% calcium aluminate mortar, made not only with calcium aluminate cement, but also with calcium aluminate aggregates. This unique chemistry provides the best resistance possible to H2S biogenic corrosion. The surface pH is also stabilized around 3.8, and the weight loss after 9 months is 12%, the lowest weight loss of all series put at test. The Fraunhofer test is an accelerated test to evaluate, within 1 year, the MIC resistance of various building materials and their capacity to resist severe H2S biogenic corrosion. The results presented here show that the corrosion rate of calcium aluminate concrete is 5 to 10 times lower than OPC concrete, even when it is enhanced with silica fume or pore blocker admixtures.